All right, Physics 11. This is going to be our next lesson. Following our lessons, in previous lessons we've done a lesson on work, right? And we talked about how work is, using an equation where you take force and you multiply it, force parallel, to displacement traveled, and we can calculate work that way. We've looked at when situations where work is actually not done, right? Because either you're not moving the object or it's not parallel to the motion. In our last lesson, we looked at situations where force was being applied at an angle and how we need to apply various different trig ratios along with Newton's laws to be able to determine what actually is that force of either friction or applied force, etc. And that can come into play later in Physics 12 with looking at work done at an angle there as well. And in today's lesson, what we're going to be doing is looking at the concept of kinetic energy as well as the work-kinetic energy theorem. Okay, so we've already looked at the work aspect of it. Today we're going to look at the kinetic energy aspect of it and then combine the two with the work-kinetic energy theorem. Okay, so there's kind of two little lessons happening in one. Both are relatively short, so it would make like a decent, 30-minute lesson or so. All right, so let's start with kinetic energy. Okay, so when we talk about kinetic energy, if you think about what the word kinetic means, it actually just means movement, right? So by defining kinetic energy, we're talking about the energy that an object possesses by virtue of being in motion. Okay, so we did briefly discuss different types of energy when we kind of started this little section, about kinetic energy, potential energy, and mechanical energy. Okay, so kinetic energy is the energy that an object has while it's moving. Potential energy would be something that an object has while it's still at rest, right? Particularly while it's being held, particularly up. We'll look specifically at gravitational potential energy in another lesson. Okay, but kinetic energy is the energy that an object has while it's in motion. Okay, so the kinetic energy formula relates its mass and its velocity, right? So the actual equation there is 1/2 times mass times velocity squared. Okay, so mass again is measured in kilograms, velocity being measured in meters per second, and you'll notice here that kinetic energy is measured in joules, right? Now, notice that joules is also a unit we used when it came to work. So I just briefly want to kind of look at a bit of a unit analysis here to give you an idea of what's actually happening and why these are actually the same units, okay? So previously, we discussed that work was equal to force parallel multiplied by displacement. We knew that force was being measured in newtons and displacement was being measured in meters, right? So work was considered a newton times a meter, which we then defined as a joule. Okay, so that was kind of what we had already going on. Now what we're saying is that kinetic energy is also measured in joules, right? But how does that work? Because it's not force times distance. We're saying it's a relationship between mass and velocity. So let's take a look at how that equals out to the same unit. So we're saying that kinetic energy is equal to 1/2 times mass times the velocity squared. So we're just going to replace things with their actual units and what they're being measured in. So mass is being measured in kilograms, and velocity would be measured in meters per second, and that's being squared. Okay, so the 1/2 really doesn't do much of it. It's just a constant, right? It doesn't have any units at all, right? So what you'd end up having there, just looking at the units, is kilograms times, since you're squaring this, it would be times meters squared divided by seconds squared, right? Because you're squaring both the meters and the squares down there. Now remember, when we first started our unit on force, the units for force was a newton. And force was defined as the amount of energy that it would take essentially to move, a newton was to move 1 kilogram, to accelerate 1 kilogram, 1 meter per second squared, right? So a kilogram times meters per second squared, that in and of itself is a newton, okay? And we can get that from this here, right? Because kilogram we can take one of the meters from the meter squared and we can use the s squared, right? So there's your kilogram times meter per second squared, right? Moving 1 kilogram, accelerating 1 kilogram, 1 meter per second squared, right? Being defined as a newton. And the only thing that we have left here, right? If we use the kilogram and the second squared and one of the meters to create a newton, what we have left is just meters. So what you notice here is what you get is newtons times meters, which is the exact same units that we have here. So once again, your kinetic energy is measured in joules. Okay, So both of them are being measured in joules based on your unit analysis, and that's what's going to allow us in a few minutes to look at our work-kinetic energy theorem, because if they're measured in the same units, we'll be able to combine them to work together to solve other missing variables. Okay? All right, going back to our slides. Okay, so this is the formula we're going to use. The EK is equal to 1/2 mv squared. So we'll just look at a couple sample problems and then get into the other section on the work-kinetic energy theorem. So the first one, if we have a 0.200 kilogram hockey puck that's initially at rest and is accelerated to a speed of 27.0 meters per second, calculate the kinetic energy of the hockey puck when it's at rest and when it's in motion. Okay, so what we're doing in this case is just using that formula, right, where EK is equal to 1/2 times mv squared. Okay, now this is fairly straightforward because in part A, it's being asked to find the kinetic energy when it's at rest. Well, if something's at rest, its velocity is 0, so it almost doesn't matter that the mass is 0.2 kilograms, because you're going to be multiplying it by a speed of 0 meters per second squared, and then anything multiplied by 0 is just going to give you 0. So obviously the kinetic energy of an object at rest is always just going to be 0 joules. Okay? However, for part B, we have been given a velocity at which it reaches. Okay? So we're kind of going to ignore the fact that, you know, it obviously has to accelerate to that speed, but then we're going to think, okay, well, if it's a hockey puck going on ice, it's then on a relatively frictionless surface, so it's going to maintain that speed until it reaches another opposing force, right? So what we can do here is say the kinetic energy of the puck once it's in motion is that 1/2 times the 0.2 kilograms multiplied that speed, and it gets up to, what does it say, 27 meters per second, right? So we use 27 meters per second squared, and then we can just multiply all of that, right? Just by saying 1/2 times 0.2 times 27 squared, and what you get is a value of 72.9 joules. Okay? All right, so again, what we needed there was 3 sig figs based on the question. Okay? Pretty sure anyway. Yeah, so 3 sig figs, right? So our we use 3 sig figs there, and the kinetic energy after the puck has accelerated. So again, note that it's after we've achieved that speed, right? So we're just kind of worried about that aspect of its motion, not the, oh, well, what about the, you know, energy while it was accelerating? That's not what we're concerned about in this particular case, okay? All right, let's look at a second problem, right? Just to kind of get an idea of manipulating that formula. So in this second problem, what we're looking at is a 0.370 kilogram ball has a kinetic energy of 1.70 joules as it rolls down a sidewalk. Calculate the velocity at which the ball is rolling. Okay, so again, we're assuming that it's rolling at a constant velocity here, and we're going to use our kinetic energy formula because it's being told that the ball does in fact have kinetic energy. Okay, so again, what we do is we're saying we know the formula is 1/2 mv squared. We've been given that the mass of the ball is equal to 0.370 kilograms, and we've been given that the kinetic energy of that ball is 1.70 joules, and we've been asked for what is the velocity. So we can rearrange this equation to get v by itself. So I'd start by dividing both sides by 1/2, which is the same as multiplying both sides by 2. Then I would divide both sides by m. And then I would just need to square root the velocity. Okay? So what I would just need to do at this point, now that I've rearranged the formula to solve for v, is substitute the 1.70 joules in for EK and the 0.37 kilograms in for m. So I would have the square root of 2 times 1.70 joules divided by 0.370 kilograms, and then square root it. Right, so when you do all of that, you get a value of 3.03 meters per second. So the ball would be rolling down the sidewalk at a speed of 3.03 meters per second, given that it has this mass and it has this much kinetic energy. Okay, so it's just, again, just a quick little showing you how you could rearrange the formula to solve for a missing variable there. All right, so that, like I said, that was a super quick little section, right? 10 minutes, and we're already done with just kind of seeing some problems about what kinetic energy is. So there's a worksheet specifically on kinetic energy, and you can try those problems if you'd like first, or you can finish watching this video and then just try both sets of questions, this one and the kinetic work energy theorem, and then go from there. Okay, so as mentioned, we've already looked at work. Now we've seen kinetic energy, and because they're all measured in the same units, we can kind of connect them similarly to how we connected momentum and impulse, right? Where momentum, or impulse, sorry, was like the change in momentum of an object, okay? Work is the change in kinetic energy of an object, okay? So like I said, the work-kinetic energy theorem is the relationship between the act of doing work on an object and the resulting kinetic energy. And if you think about that, it does make sense, because if you're going to do work on something, it's obviously going to change its kinetic energy. If you're causing it to move, right, which by definition of work you are causing it to do, you're having a force being applied and it's moving a particular distance, then if you're moving, you have to have some sort of velocity, which means if you're starting from rest and then you're moving, you've got two different velocities of that same mass. Okay, so you are going to get changes in kinetic energy, right? And then the change in that kinetic energy is the work done. Okay, so basically what we're saying here then is that work is just equal to the change in kinetic energy. So it's the final kinetic energy of the object minus the initial kinetic energy of the object. So you're using the same formula for kinetic energy, 1/2 mv squared, but this would be like V2 and this would be V1, or Vf and Vi, right? And this could be EKF minus EK1, or EK2 minus EKI. I typically like 2 and 1 work, I and F work. Just be aware that it might be different on particular questions, right? Or different textbooks might show you different formulas, okay? So the notes here have 1 and 2, and then when I do them on the board, I'll use I and F just to kind of let you see different ways of doing them, okay? So let's just do a couple practice problems with this one as well. So in this first one, a physics student does work on a 2.5 kilogram curling stone by exerting 4.0 times 10 to the 1 newtons of force horizontally. So in this case, if we're pushing a curling stone, that is in the direction of motion, okay, over a distance of 1.5 meters. Calculate the work done by the student on the curling stone, and then assuming that it started from rest, calculate the velocity of the stone at the point of release. And once again, since we're dealing with curling and it's on ice, which is essentially a frictionless surface, again, we know it's not totally, but if we're assuming frictionless at, those first little bit that it's been moving, that velocity at, like, the final velocity would be the same velocity as when it was first released. All right, so let's just get into that. All right, so again, listing the things that we have for this practice problem, we know that the mass of the curling stone is 2.5 kilograms. We know that the force exerted on that stone was 4.0 times 10 to the 1 newtons, and we know that it travels a distance, or a displacement, of 1.5 meters. Okay, so the first thing is we are being asked about what's the work being done on that, work being done by the student on that curling stone. Okay, so work was that formula of force parallel multiplied by displacement, and it is moving 1.5 meters horizontally, so the displacement and the force are acting in the same direction. So we can just go ahead and multiply that of 4.0 times 10 to the 1 newtons multiplied by the 1.5 meters, and that gives us a value of 60 joules. Right, now we get 2 sig figs, so notice that I'm just placing the decimal there to indicate that this 0 is significant. So the work done by the student on the curling stone over that period of 1.5 meters is 60 joules, okay? And again, that kind of goes to what I was saying about how, like, in that first little bit of motion, right, it probably wouldn't change velocity very much, so we can still assume that that final velocity at that point would be the same as what it would be when they first left the curler's hand, okay? So that brings us to part B, where, like I said, we are being asked for what is the velocity. And in this case, it's kind of like the final velocity, because VI, the initial velocity, is 0 because we're being told to assume that the curling stone was at rest. Okay, we already have the mass, and we know the velocities. And we actually know the work here, right? So this is where you can combine the work-energy theorem by stating that work is equal to EKF minus EKI, okay? So work is going to equal that 1/2 mvf squared minus 1/2 mvi squared. And continuing with just rearranging that formula, right, we're interested in mvf. So if we keep on going over here, we can take this entire term and bring it over. So we would have work plus 1/2 mvi squared is equal to 1/2 mvf squared. And then we would need to divide by 1/2, which is the same as multiplying by 2. Okay? And then divide by m, and then square root. So you would get the following. Okay? Right, so this is what we would have that we could plug into to now solve for that final velocity. Now work we already solved for in part A. We know that that value is 60 joules. And if the curling stone is initially at rest, this value of VI is 0, so this entire term becomes 0. So it's just 60 plus 0, so it just remains as 60. And then we're dividing by the mass, which is the 2.5 kilograms, and then we can square root. Okay, so our value here, we would take 2 times 60 would be 120. We divide 120 by 2.5, and then we would square root. And all of that, and we only get 2 sig figs, gives us a value where VF would equal 6.9 meters per second in this case. Okay. So again, using a combination of the work equation, which I've already erased, right, that we've already learned, and the kinetic energy equations, and then the combining of the work-energy theorem, you can put things together to find missing pieces like velocities or mass or distances, right, depending on what you're being asked to find, okay? So we'll look at one more practice problem, okay? So there's your solutions, the 60 joules, and then being able to solve to get your velocity. All right, so looking at this one, you've got a 75 kilogram skateboarder. That includes the skateboarder and the board, initially moving at 8 meters per second. And the skateboarder exerts an average force of 200 newtons by pushing on the ground over a distance of 5 meters. Find the new kinetic energy of the skateboarder if the trip is completely horizontal. So no jumps, no losing of the board. It's just you're currently going at 8 meters per second. You're pushing on the ground with your foot to go faster. What energy do you have after you've moved 5 meters by doing that 200 newtons of force through the pushing? Okay, so if we're thinking of this, I'll go back to the video session. Right, once again, we start by listing the things that we know. So we have that the mass is 75.00 kilograms, right? That just means we're going to be using sig figs here of 4. We know that the initial velocity of the skateboarder is 8.000 meters per second. We know that the average force exerted is 200.0 newtons, and that the distance or the displacement covered is 5.00 meters. And we are interested in what is the final kinetic energy. So we're basically being asked for what is EKF. Okay, so we can first think about, well, what's an equation that involves EKF? And it's that work-kinetic energy theorem, where work is equal to EKF minus EKI. So to get EKF, we would just need to add EKI to both sides. So work plus EKI will equal EKF. Okay, well, how would we find work done? Well, work is the equation of force multiplied by displacement. Okay, and how would we find EKI? Well, that's a kinetic energy, so 1/2 times mass times velocity squared. All right, well, this we can do a side calculation, right? Force times displacement. We have both of those pieces of information. So our work is just going to equal our 200 newtons multiplied by our 5 meters, and that gives us 1,000 joules of work being done, okay? Now, we can also figure out what our EKI is because we also have information about mass and the initial velocity, right? So our EKI, which is our 1/2 times mass times velocity initial squared, is going to equal 1/2 times our 75 kilograms. I'm just dropping the decimals because I don't have space on the board, multiplied by our 8 meters per second squared. So if you do that, right, 8 squared multiplied by 75 and then cut it in half, you get a value that I forgot to write on my sheet. But 0.5 times 75 times 8 squared, you get that this is a value of 2,400 joules. Okay, put the decimal there to show that we get all 4 sig figs. Okay, so then we kind of go back here and say, well, our EKF is going to equal our work plus our EKI. So we have work done was 100 joules. We have that the initial kinetic energy was 2,400 joules. So our final kinetic energy is going to be 3,400 joules. Right? Again, makes sense if you start off with kinetic energy of 2,400 joules and then you do 100 joules of work on top of that, well, then your final kinetic energy will now be 3,400 joules, right? Because you've added kinetic energy to that system, right? You were already in motion, you already had kinetic energy, you've done extra work, right? Which has now increased your level of energy and it's increased it in the kinetic sense, right? You're now moving faster, so you have more kinetic energy. So our final kinetic energy here is 3,400 joules, right? And then if we wanted to, we could expand on this question again and then say, okay, well, how fast is the skateboarder moving now? Well, you know that EKF is going to be 1/2 times mass times velocity squared, and you have mass, so it would just be a divide both sides by 1/2, divide both sides by mass, square root, and you get your velocity. Okay, so that's kind of showing how we can use both the equations about work and kinetic energy and the work-kinetic energy theorem to solve for missing pieces of information in a question. Okay, and yeah, so there's your solutions typed out there. There you go. And then you've got a few questions to do, I think 5 questions there to do from the textbook, and I'll post that document for those of you who don't have your textbooks with you. If you do have your textbooks with you, remember that there are page discrepancies, so just potentially just use the one that I'm posting anyway. Okay, so you've got a worksheet just kind of focusing on kinetic energy, and then you've got these textbook questions that focus on the combination of work and kinetic energy using the work-kinetic energy theorem.